Hi, welcome to Organic Chemistry. In this presentation, I'm going to look at alkenes. I'm going to look at their properties, I'm going to look at how to synthesize alkenes, and I'm going to look at the reactions of alkenes. Due to the large size of this unit, I am going to break this file up into several pieces for ease of conversion to a format that I can share on YouTube. This particular subsection will look at just the structure and property of alkenes. View from the first semester of organic chemistry. You know that an alkene involves a carbon-carbon double bond, and we get a carbon-carbon double bond because when you're drawing a Lewis structure, for instance for C2H4, you come to this point where you've only got 7 electrons, valence electrons around this carbon and 7 around this. And of course we all know that the solution is to pair up these 2 electrons to make a second shared pair. And so we get a double bond. When we look at the orbitals involved in a carbon-carbon double bond, we see that we've got trigonal planar arrangement around a carbon, so we've got sp2 hybridization. We've got 3 sp2 hybridized orbitals at 120 degrees to each other. And then there's a p orbital that's orthogonal to that trigonal plane. When we bring up another sp2 hybridized carbon, the overlap of those 2 sp2 orbitals that are pointing directly at each other makes a sigma combination. But we also get a second combination, the overlap of the 2 parallel p orbitals, to make a pi combination. So a double bond is made of 2 parts, a sigma part and a pi part. This pi bond leads to, one of the consequences of a pi bond is that you have restricted rotation. Because if I was to rotate the carbon on the left relative to the carbon on the right, that would necessarily involve breaking this interaction between these 2 p orbitals. And that's breaking a bond, so that's not a conformational change, that's a chemical reaction. We would actually have to put in energy to do this. We'd have to put in a specific wavelength of light, for instance. So we've got 2 possible isomers, the trans, which is known as entgegen, or E isomer, and the cis, which is known as zusammen, or Z. And these are stereoisomers of each other. I'm not going to belabor naming very much, but just remember that when we've got alkenes, we have to name, we're going to treat this like naming alkanes. That is, we're going to use a prefix to say how many carbons that we have, and then a suffix in alkanes ended in ane to say that we had carbon-carbon single bonds. But we're going to end in ene to signify that we've got a carbon-carbon double bond. So for instance, this first compound has 3 carbons, prop, and it's got an alkene, so it's propene. But in this second molecule, we've got the double bond between the second and third bond. And there's actually a couple of possibilities. It could be between the first and the second, or the second and the third, and the third and the fourth. We're going to have to name where the alkene comes. So not only do we have to name where branches are, this one is 2-methyl-2-butene. We have to name where the alkene is. And notice I don't say that the alkene is between 2 and 3, I say it starts at position 2. It's because it's superfluous to say which the second carbon is, because it always has to be between 2 adjacent carbons. So you name the first carbon of the alkene. And by the way, there's 2 ways that are acceptable to name this. We'll call this either 2-methyl-2-butene or 2-methyl-but-2-ene, and either one of those is fine. I will more likely say 2-methyl-2-butene. Let's take a look at this third example. And notice here, okay, we've got an butene. The alkene, the double bond, is between positions 2 and 3. And if I number from right to left, 1, 2, 3, 4, my branch is at position 2, bromo. So it's 2-bromo, 2-butene. But there would be 2 stereoisomers, because if I was to switch this bromine and this carbon group, I would get my carbon part like this and a bromine off to the side, as opposed to my carbon part like this and the bromine off to the side. So we have to say which stereoisomer we have. To name stereoisomers, we look at each end of the double bond, and this end has a bromine and a carbon. And of those two, which has the higher atomic number? Bromine. So this gets priority. At this end of the double bond, I've got a carbon and there's an implicit hydrogen here. So carbon wins. So then we say, are the two groups that have the higher priority, one from each end of the pi bond, on the same side or the opposite sides? If they're the same, that's zusammen in German, is together. If they were on opposite in German is entgegen. So we would say that this one is zusammen, or Z, 2-bromo, 2-butene. If we have more than one pi bond, more than one double bond in a molecule, we have to say diene, and of course we have to say where each of those is. So in this molecule, it's 7 carbons long, hept. I've got alkenes, double bonds, at 1, 2, 3, 4, 5, 6, 7. So we've got one starts at position 2 and one starts at position 4. So this is 2,4-heptadiene. And we also have to say the stereochemistry of each of my pi bonds. So the pi bond at position 2 has an E stereochemistry, and the pi bond at position 4 has an E stereochemistry. And so this is the proper syntax for this. Or you could say 2E, 4E, hepta, 2,4-diene would also be correct. All right. Let's talk just a moment about the energies of various alkenes and comparing them. Now, I'm not going to get into the specific reaction right now, but we will before the end of this presentation. But I can take an alkene and I can add 2 hydrogens. And I'm going to add one to one carbon and one to the other carbon. Now notice this is C4H8, which has 1 degree of unsaturation, one alkene. But if I was to add 2 more hydrogen atoms, I'd get C4H10, which has 0 degrees of unsaturation, no rings and no pi bonds. In other words, I would take this double bond, I'd put 1 more hydrogen here, and 1 more hydrogen here, and so I'd get a CH3 on this end and a CH2 here. This would be a carbon-carbon single bond. Notice if I did the same thing here, and the same thing here, in each case, I get the exact same product, butane. So if I take 1 butene and add 2 hydrogens, 2 hydrogen atoms, or E, in order, Z or E to butene, I'm going to get the same reaction product in each case. We'll talk about the details of this type of reaction. It's called a hydrogen reduction. It involves a catalyst, and we'll talk about that a little bit later on in this presentation when we're talking about the reactions of alkenes. But for now, I'm not interested in how that reaction works, because I want to look at the thermodynamics. And remember, thermodynamics is just about comparing the starting materials to the products, and talking about the energies of those. And we can actually measure these in lab. There's a process, an experimental process called calorimetry that allows you to measure the energy of different reactions in the lab. And you would find that each of these reactions is downhill. That is, they're exothermic. But they're downhill by different amounts. The first one is downhill by 30, the second one is downhill by 29, and the third one is downhill by approximately 28 kilocalories per mole. But if you end at the same place, and you go down differing amounts, you must have started at 3 different energies. Essentially, we've got 3 different slopes that all end at the same place, but we know how far down it is to get from the starting material, in each case, to the product. And if I know that the starting material for the terminal alkene is more exothermic going to the butane than the internal, this is the alkenes where the pi bonds are in the middle of the chain, I know that this had to start at a higher energy place, since they all have to end at the same place. So one conclusion I can make from this is comparing alkenes, I can see that terminal alkenes, and terminal alkenes are where the pi bond is at the end of the chain, the terminus of the chain, are generally higher in energy than the internal alkenes. And in fact, I can go further with this, and I can just find that in general, the more carbon groups around an alkene, the more stable, the fewer carbon groups, the less stable. And by carbon groups, I mean, if you look at this, here's the alkene portion, And attached to the sp2 hybridized carbons, there's a hydrogen, a hydrogen, a hydrogen, and a carbon. So this one has one carbon directly attached to the sp2 hybridized carbons. In this case, we've got my sp2 hybridized carbons here, and this one's attached to a hydrogen and a carbon, and this one's attached to a hydrogen and a carbon. So we would say that there's two carbon groups around this alkene. And in fact, the trend continues. If there's 3 carbon groups or 4 carbon groups, those are even more stable. There's also a difference between the cis and the trans, or the Z and the E. And it turns out that the Z is a little higher in energy than the E. And we might expect that based on what we know about steric interactions. When I've got 2 groups that are larger, the methyl groups, here versus here, as compared to here versus here, and I bring them closer to each other, that's going to raise the energy. We saw this as long ago as when you talked about the rotations of substituted ethanes. And we see that this one, the cis version, has more steric interaction between these methyl groups than the trans version. And so we get a higher energy starting material. So we can roughly compare alkenes, and we could say, for one, the more carbon groups, the more stable. The fewer carbon groups, the less stable. And we can also say that cis are higher energy, less stable than trans disubstituted alkenes for steric reasons. Now there are some other geometric concerns. If you've got a small ring, like a 6-membered ring, you just can't have a trans double bond. Take out your model set and try and build it, and you would find that it's just way too strained. The bonds just don't work. The smallest ring that can have a double bond in it is an cyclooctene, but even that is a highly strained double bond, and it would rather be a cis double bond. Once you get to much larger rings, then you can build rings with trans double bonds, but for small rings, they're definitely out. It's also true that when you've got a bicyclic species, where you've got 2 small fused rings, such as this 2-2-1 bicyclic system, you can't have a double bond at what's called a bridgehead position. Again, if you pulled out your model set and tried to build this model, even though you can draw it, on paper, if you tried to build the model, you would find out that it's just way too strained. It just doesn't work. So sometimes there are steric concerns or strain concerns as to which alkenes are possible to make in a given situation.